steady-state conduction and convection systems. And these are, really fundamental concepts in chemical engineering. So if you're a first-year chemistry student, this is all about how heat moves through a solid object. And crucially, how we can engineer surfaces like fins to get rid of that heat efficiently. Okay, first up is steady-state conduction, but with a twist: internal heat generation. Think about something like an electric wire, where heat is being produced inside it. What you're learning here is how to find that maximum temperature right at its center, because if you don't, that wire could overheat and fail. Super important stuff. Second, we get into convection systems, which is really all about using fins. The key here is an energy balance. You're basically saying that whatever heat is conducted into a tiny piece of the fin has to equal the heat that's lost to the air around it through convection. And from that simple idea, you get the core equation you need for designing any fin. And finally, we look at fin performance. Because how well a fin works really depends on what's happening at its tip. Is it super long, or is the end insulated? You have to look at these different boundary conditions. This all leads to calculating the fin's efficiency, which is just the single best number to tell you if adding that fin was actually worth it. Let's dive into more detail.
Have you ever wondered how our most powerful gadgets, from our gaming laptops to those amazing superbikes, don't just melt? Well, the answer is actually hiding in plain sight. Today, we're going to dive into the unsung heroes of cooling, the humble but brilliant heat fin.
Okay, so let's really jump into this with the big question. How do powerful things stay cool? It is a huge problem. When you generate power, whether it's processing power in a computer or horsepower in an engine, you create a ton of waste heat. And that heat has to go somewhere, right? Let's look at a few examples.
First up, think about your laptop CPU. It's this tiny little chip, maybe the size of your thumbnail, and it's performing billions of calculations every single second. All of that electrical energy creates this incredible amount of heat, all focused in one very tiny spot.
Or how about a motorcycle engine? You know those iconic metal ridges you see sticking out? Well, they're not just there to look cool. They are a classic, super visible example of this cooling technology in action, battling the insane heat from internal combustion.
And it's not just about computers and engines. Even something really modern like a high-power LED light, the kind they use in stadium lighting or projectors, generates so much heat that without the right cooling, it would literally burn out in seconds.
So what's the solution to all these completely different heat problems? Well, it's this incredibly simple yet totally brilliant idea called an extended surface. But you and I, we just call it a fin. It's basically just a piece of metal that sticks out from a hot object to help it cool down. But how does it actually work?
The magic of the fin, and it really is kind of magic, comes down to a balancing act. It has to perfectly manage two fundamental jobs in the world of heat transfer. It's moving heat in two different ways at the exact same time.
So a fin has two crucial jobs. First, you've got conduction. This is heat traveling through the solid metal of the fin itself. Imagine it's like traffic moving down a highway, going from the hot base out toward the cooler tip. And then you've got convection. This is the heat leaving the surface of the fin and getting carried away by the air around it. Think of these as all the exits along that highway. So for a fin to be great, it needs both: a super fast highway for the heat and plenty of exits for that heat to escape.
So how do engineers actually figure out this balancing act? Well, like they always do, they tell its story with mathematics. And they do it by looking at a tiny imaginary slice of the fin and just watching what happens to the energy as it moves through. And this is all built on one of the most fundamental principles in all of physics: the energy balance. For any system that's running at a steady temperature, it is beautifully simple. The energy that comes in must equal the energy that goes out. That's it. No magic. It's just accounting for heat.
Let's apply that to our tiny little slice of the fin. Okay, so heat conducts into the left side. Then a slightly smaller amount of heat conducts out of the right side. So you gotta ask, where did the missing energy go? Well, it escaped. It left from the surface into the cooler air through convection. This gives us our perfect balance. Energy in equals the energy out plus the energy that was lost to the air. And that simple energy balance, when you write it in the language of calculus, turns into this: the governing differential equation for the fin. Now don't worry, don't panic. We are not going to solve this today. What's so important to see here is that this one single equation tells the fin's entire story. It can predict the exact temperature at any point along its surface, just based on its material, its shape, and the air around it. It's amazing.
But, every story has different endings, and it's the same with a fin. It's kind of like knowing the rules at the end of a game. What's happening at the very tip of the fin changes the outcome for the whole thing, and engineers have a name for these different endings: boundary conditions.
And there are 3 common scenarios they usually consider. Case 1 is sort of the perfect world theoretical idea, an infinitely long fin. The tip gets so far away that it cools down completely to the same temperature as the air. Case 2 is way more realistic. It accounts for the heat that also escapes from the flat tip at the very end. And finally, case 3 is a really useful shortcut, especially for long, thin fins, where we just assume the tip is insulated and doesn't lose heat. It simplifies the math a lot, and honestly, it's often surprisingly accurate.
So we get the physics, we've seen the math, but this all leads to the most important question for any engineer, right? Is this fin any good? How do we actually grade its performance? Well, we use a metric called fin efficiency, and it's really just a simple ratio. You take the actual heat the fin manages to transfer, and you divide it by the absolute maximum amount of heat it could possibly transfer. And that perfect theoretical maximum, that would only happen if the entire fin, from its base all the way to its tip, stayed just as hot as the surface it's attached to. The easiest way to think about it is like a performance score, right? Out of 100%. A perfect 100% efficient fin would have the exact same temperature all the way down its length. But in the real world, fins always get cooler as you move toward the tip. So, a lower efficiency score just tells us that the tip is getting significantly cooler than the base, which means it isn't transferring heat quite as effectively as it could.
And remember that big master equation we saw earlier? Well, this is where it pays off. It leads directly to practical tools, just like this one. This formula right here calculates the efficiency for that insulated tip fin we talked about from case 3. An engineer can just plug in the material, the shape, the air conditions, and get that performance score instantly. It's the direct link from the physics to the practical design.
So, what's the big takeaway here? What does this all mean? Well, first, fins are a brilliantly simple solution to the absolutely crucial problem of getting rid of heat. Their performance is this constant, delicate balancing act between conduction and convection. We saw that a single master equation can actually model this entire balancing act. And maybe most importantly, fin efficiency isn't just a grade, it's a powerful design tool. It's what tells an engineer how to make trade-offs between cost, weight, and size. This is the physics that drives real-world engineering every single day. So from just a simple strip of metal, we get this whole story of conduction, convection, and calculus that literally keeps our modern world running. The fin is a perfect example of a simple design hiding some incredibly powerful physics. Which, it makes you wonder, doesn't it? What other everyday objects out there are unsung engineering heroes? Thanks for watching.